Okay, first of all, I have an objection against Tom-san's statement in this conference. If you remember the Tom-san's presentation in the first day of this conference, you just mentioned that Nature rejected my recent 3 papers. Then somehow, he stopped here, and he didn't mention anything after these things. So this is really unfair, so let me emphasize the important things here. So eventually, let me emphasize that all of these 3 papers are published in the different journals, so thank you very much. Then I think it's a fair way to say so. Anyway, so my talk today is based on this final recent latest paper appeared in the RIS recently. Okay, let's move on. The title is Young Galaxy Cluster in the Old Universe. By the way, my name is Tetsuya Hashimoto from Tsinghua Dashi in Hsinchu in Taiwan. This work, my talk is based on this work in collaboration with these people. Okay. So this is outline today's my talk, which includes 5 different parts, starting from the introduction, sample selection. In my talk, I use the Sloan Digital Sky Survey data release 7 to identify galaxy clusters. And then as a result, we discovered a very strange galaxy cluster, which includes too many star-forming galaxies in contrast to the theoretical model prediction. Okay, then let me discuss. And then in the end, I will conclude this talk. Okay, so in the universe, there are 2 different types of galaxies. It's very simple. Star-forming galaxy, blue star-forming galaxy, and red quiescent galaxies. This is star formation rate as a function of stellar mass of galaxies. So 1 dot corresponds to 1 galaxy in this parameter space. As you can see, there is a clear bimodality in this figure. Blue star-forming galaxy here and the red quiescent galaxy. It is well known that these blue star-forming galaxies evolve into the red quiescent galaxies by quenching star formation. So this is well known. It is also well known that this evolution is quite effective, especially in the galaxy cluster environments. So as a consequence, if we look at the local galaxy cluster environment, we can see member galaxies of local galaxy cluster is basically dominated by red population. So I just show the example of local galaxy cluster, which is taken from Abel cluster at radius 0.18. So as you can see, basically member galaxies are red here. Then blue fraction, which is a number fraction of blue star-forming galaxies in cluster environment, is typically as small as 0.2 observationally in the local universe in the massive cluster environment. So this is observational evidence. So, however, in previous studies, some blue clusters are reported. So blue cluster means galaxy cluster which includes a lot of star-forming galaxies in contrast to theoretical physics. But this is still okay. This is okay because for less massive galaxy clusters or less dense galaxy clusters, so model also predict high blue fraction. So this is okay. High blue fraction for less massive galaxy cluster is okay. Model also predicts. But by going to this way, we cannot really understand how blue cluster is strange in the local universe. So what we did in this talk is something like this. So we only focus on very, very massive galaxy cluster, very, very high dense galaxy cluster. Then we can immediately recognize that this galaxy cluster is really strange because models never predict high blue fraction for massive galaxy clusters. So this is what we did. Actually, we used the Sloan Digital Sky Survey to identify this kind of galaxy cluster in my talk, in this work. So this is most important figure in my talk. So blue fraction, that is number of blue star-forming galaxies, number fraction of blue star-forming galaxies in cluster environment in y-axis as a function of velocity dispersion of each galaxy cluster. Because Sloan Digital Sky Survey has a spectroscopic data, so we can calculate velocity dispersion of individual galaxy clusters. At the same time, we can calculate the dynamical mass from this velocity information. So in this diagram, so one dot now corresponds to one galaxy cluster. As you can see, okay, more or less, typically massive, okay, and also I forgot to mention about this. I just only pick up galaxy clusters in very, very high dense region environment, which is this is higher than H sigma. Then for this high density, the massive galaxy clusters, typically they show blue fraction of 0.2 more or less. So this is natural things. But in my talk, I will emphasize that we found that this outlier, this is the 4 sigma outlier in terms of blue fraction compared with the galaxy clusters identified with the exactly same criteria. So this is blue cluster we found, which shows very high blue fraction, yet hosted by very massive dark matter halo, which is 10 to the 14 solar mass. This value is kind of massive end of dark matter halo in the local universe. This is really weird. So here, let me just show example of member galaxies in normal local massive galaxy cluster. I just pick up galaxy clusters at the same redshift and the same dynamical mass. So this is a kind of archetype of massive galaxy cluster in the local universe. So as you can see, basically member galaxies are dominated by blue galaxies. So I just marked by dominated by red galaxies. I marked by red circle here. Next, I will show you the member galaxies of blue cluster that we found this time. So the member galaxy looks like this. This is really different from the archetype or local massive galaxy clusters. So actually, more than half of the member galaxies are categorized into blue star-forming galaxies by our definition. So why this blue cluster is so blue? So in order to understand how strange is this, we compared this blue cluster with the semi-analytic model prediction of galaxy formation. So here we pick up 2 different galaxy semi-analytic model because they have enough calculation volume to compare in a statistical way. So one is a galactics, and another is a Newton DC here. Then we apply the exactly same criteria to identify galaxy cluster to these modeled galaxies. So they have modeled galaxies in catalog. So I just apply the exactly same criteria to identify galaxy clusters in modeled universe. Then this is again blue fraction as a function of velocity dispersions. But one dot is one galaxy cluster here in modeled universe. So as you can see, basically model doesn't predict very high blue fraction, blue outlier in this diagram. If I compare with blue fraction, blue galaxy cluster that we found here, it's located here. That is still more than 4 sigma away from the median line of massive galaxy clusters. So this indicates that standard framework of semi-analytic model of galaxy formation cannot explain this unexpectedly high blue fraction of blue cluster. Okay, here there may be hints in the large-scale structure around the galaxy cluster. So this is 80 megaparsec times 80 megaparsec area on sky around the galaxy, this blue cluster. So blue cluster is located at the center of this diagram. It's very tiny in this figure. And then this box is just a zoom in this region. Then I only plotted the galaxies at the same redshift as the blue cluster here. Then contour corresponds to the number density contour in this galaxy distribution. Then blue line corresponds to filamental structure identified by previous study here. Then in zoom-in box here, galaxy cluster is located here. The color, now color corresponds to the number density environment in this figure. It's not star-forming activity. This is the number density is high here. And the dashed line is showing the dynamical radius of this galaxy cluster. And the solid circle here corresponds to 8 sigma high density region on this sky map. Then we found that, as you can see, there is a large scale filamentary structure surrounding this blue cluster. At the same time, we also found that along this filamentary structure, blue fraction, this is a blue fraction map on the same area. Blue fraction is also high along this large scale filamentary structure. So this indicates that probably there are a lot of gas along this filamentary structure. Then probably this gas is accreting onto the central blue cluster, which probably triggers the active star formation in blue cluster. So this is the observational suggestion. However, in terms of simulation, this kind of accretion onto the large dark matter halo might be difficult because of biliary shocks. So in simulation, biliary shocks prevent the cold stream. So this kind of cold gas accretion may be heated by biliary shock. Biliary shock happens because of the strong gravitational potential wave of dark matter halo. So for cold streams, this cold accretion of gas to survive in cluster environment, so this cooling time scale needs to be lower than shock compression time scale. So assuming this simple condition, so Decker et al. Calculated a parameter space where cold stream can survive. So this is dark matter halo mass as a function of redshift. Then in blue shaded region, so cold streams can survive. Cold stream can overcome the biliary shock. But in red region, this parameter space, biliary shocks overcomes the cold stream. That means cold stream is heated by biliary shocks, and then there is no way to form stars. I mean, there's no way to enhance the star activity in this parameter space. So, but actual location of blue cluster that we found is located here. That is way away from this blue shaded region. So this means that, okay, observationally, so this cold stream might be suggested. It maybe happen in this blue cluster that enhance the star activity in this strange galaxy cluster. But in simulation, this cold stream already disappeared in simulated local universe. So this is a mystery we found about this blue cluster. So let me conclude. We discovered a blue cluster at redshift 0.46, which shows unexpectedly high blue fraction, number fraction of blue swarming galaxies, yet hosted by massive dark matter halo, which is 10 to the 14 solar mass. Then there is no reasonable explanation to explain this high blue fraction. So that means the blue fraction we found challenges the current standard frameworks of galaxy formation and evolution in the random CDM universe. Okay, I stop here. Thank you very much.
We have time for one questions.
Just a quick one. How did you measure this halo mass of 10 to 14 solar mass in your system?
I just assume the biliary system, and I know the velocity field.
So you did the spectroscopic follow-up of all those galaxies in this blue cluster?
Not really, because I just use the strong distance survey, which is available. Yes.
Nice.
I guess one more question. One more question, is there any? Yeah.
Very nice talk. So I wonder, is this object covered by some X-ray survey so that you can check whether or not the hot gas property is different?
Actually, only the LOSAT all sky survey cover this area. And then there is a measurement of X-ray flux, but that is super low signal to noise ratio. SN ratio is kind of 1.2 or something. But anyway, there is a measurement of X-ray flux at the position of this cluster. And then if I convert this flux into the X-ray luminosity, that is consistent with local scaling relation of galaxy cluster between X-ray luminosity and dynamical mass. So, but anyway, the SN is very low, so we need for our observation.
Okay, thanks.
Okay, that's